Good evening, all. Today we are going to discuss a topic based on Young's double slit experiment. So, in Young's double slit experiment, what all things we need to learn? So, my plan is to focus on few points like interference pattern. The second point is sustained interference. The third is bright and dark band conditions. Then comes bandwidth, and finally angular width. We already made a video based on constructive interference and destructive interference where I have mentioned about the bright band and dark band conditions. So today we will be focusing basically on the other points. So we know that an interference pattern is obtained when you use monochromatic or coherent sources of light. And when you use monochromatic sources of light, that means light of same wavelength which is passing through two slits of almost zero or constant phase difference. When they superimpose, you get a pattern. That pattern is called as interference pattern. In an interference pattern, there will be a central bright fringe form followed by alternate bright and dark bands, as you can see in this diagram. So in this diagram, you can see a cylindrical source is coming. I mean cylindrical light is coming, or wavefront is coming, and then passing through two slits, generating a central bright band followed by alternate bright and dark bands, isn't it? Now that's regarding the interference pattern. And for this pattern to remain sustained means that pattern should not shift. The bright bands or the maximas and minimas should not move. There are a few conditions for that. If we can follow those conditions, then the interference pattern will be called as a sustained interference pattern. What are the conditions for sustained interference? You can see here 7 points. Number 1, two waves interfering should have same frequency and same wavelength. Number 2, amplitude of two waves should be either same or nearly equal. The third point, two sources should be narrow or close to each other. The fourth one, as expected, coherent sources. The fifth point, two sources should be of the same state of polarization. Number 6, waves should travel along the same direction. And the seventh point is that the distance between the source and the screen should be large enough. So if you follow these conditions, the pattern is going to be sustained. That means it won't move, it won't shift. Okay, so those are the conditions for sustained interference. Now you can see here the pattern once again with central bright band, and again on the both side you can see it maximas and minimas. Those maximas and minimas are called secondary maximas and minima. So it is numbered like first dark, second dark, third dark on either side. And you should understand that basically one fringe means one full bright band and one full dark band. Okay, so what you can see is a lot of fringes on the screen. So one full bright and one full dark is called one fringe. Okay. Now the width of a fringe is also basically the same thing which we will see later. And you will always end up with a central bright band because the light waves coming from two slits will superimpose always at zero phase difference or zero path difference, and that's why you get always a bright band at the center. Okay, now jumping into the conditions of bright band and dark band, which we already saw in the previous video, which is basically constructive interference and destructive interference. There we mentioned the condition for obtaining the bright band is path difference should be equal to integer multiple of wavelength, which is equal to d sine theta equal to xd over capital D, where sine theta, in that theta is the angular position of the secondary maxima or secondary minima. X is the linear position or linear width from the central maxima, as you can see in the diagram. It's the distance from that central maxima to the point P. Capital D is the distance between slit and the screen. Okay, so this is the condition for obtaining a bright band. The condition for obtaining a dark band, remember one thing, that n value will change from 0, 1, 2, 3, it goes like that. Okay, and for dark band, this path difference will be equal to the odd multiple of lambda by 2, which we can write it as 2n minus 1 lambda by 2. Once again, the remaining part is basically same, which is d sine theta equal to x d over d, and that way you can also calculate the angular position towards the secondary minimas, as well as the linear width or the linear position towards the secondary minimas. So these are the conditions for bright band and dark band respectively. Now, fringe width. Fringe width, as I already said, one full bright and one full dark is what we call as one full fringe. You can also define the width of a fringe in different way, which is what you can see here. It's the distance between the centers of two successive maxima, or between the centers of two successive minima. Okay, so that width is called as fringe width, and that distance is equal to lambda times, that's the wavelength, times capital D, which is the distance between slit and screen, divided by the slit width, small d. That way you can calculate the fringe width. Understood? So this is the formula to calculate the fringe width, and it's very important. And remember, all the fringes will be basically of the same width in interference pattern. Now, regarding the angular width, we know what angular position is, which is basically the angle formed towards a secondary maxima or secondary minima, which we have already so that in the conditions of bright band and dark band, that d sine theta part, that theta is basically the angular position. So the difference between the successive the distance between the angles or the angular positions of successive maxima or successive minima, you can call it as angular width. So basically like theta n plus 1 minus theta n. That means for an example, I can say that is the angle tilted towards the third secondary maxima minus angle tilted towards the second secondary maxima is an angular width, which will be exactly same equal to, for example, the angle tilted towards the 10th secondary minima minus angle tilted towards the 9th secondary minima. You get the same thing. That angular width formula is equal to lambda by small d equal to beta by capital D. So here what you can see, this theta is angular width. It's the difference between the angular positions. Don't get confused with the previous theta. This is actually the difference between the angular positions. The formula is lambda over small d or beta over capital D. That is angular width. Okay. Now, imagine a situation like this, that for example, we know that the screen what we are using is basically the same. The distance between slit and screen will be same. Distance between the slits, if it is same, imagine you are taking two different wavelengths, lambda 1 and lambda 2. And here what we are going to find out is the number of fringes formed. If, say, for example, M1 fringes are formed when you use the first wavelength lambda 1, and M2 fringes are formed when you use another wavelength lambda 2, provided all other physical parameters are same, then you can write the condition M1 lambda 1 equal to M2 lambda 2. It's a very important relation. You can also use this same method of writing if during coinciding cases. For example, say the 10th bright band is coinciding with when you use light of one particular wavelength, 10th bright band is coinciding with 12th bright band when you use another wavelength lambda 2, then how can we write it? So 10 lambda 1 equal to 12 lambda 2. That way you can write. Also you can write if, for example, the third bright band of a particular wavelength is coinciding with the fifth dark band of another wavelength. So how will you write it? 3 lambda 1 equal to then 2n minus 1 lambda by 2, in which you need to substitute n equal to 5. So this is basically the coinciding cases. So that way you can calculate the unknown wavelength if it's required. Also, if you use a white source of light instead of the monochromatic source of light, what you are going to get is an interference pattern which is basically colored. Definitely you will be getting the central bright band as expected, a complete white band, but then followed by colored fringes is what you are going to get. Understood? So these are the things that I need to share with you. So today we discussed about the conditions of bright and dark band, successive, sustained interference, isn't it? Fringe width, angular width, and also interference. Thank you.